Hi guys, so let's do a recap of what we covered today in class with projectile motion and two-dimensional kinematic equations. So on our cannonball picture, we drew the components of velocity. We realized that the v sub x vector was the same. And the v sub y vectors changed over time. So here you can see v sub x vectors of the same length and the same direction, and I'm just going to draw a line through them to say that they are all congruent. And my v sub x vector. So the most important things to notice on the way back down was that point E was closer to point D than point C was. Therefore, the vertical component of its velocity should have not only pointed down, but it should have been smaller. Here at point F, which was in line with point B, the velocity vectors in the y direction should have been the same size, just opposite directions. And at point G, which was higher off the ground than point A, the vertical component of its velocity vector should have been smaller than that of point A. When we connected our rectangle, and drew in the resultant velocity vectors, we saw that they didn't exactly fit directly on the dotted line. And that was because the orange vectors represented, apologies for my cough, represented the instantaneous velocity, meaning it represents the velocity exactly at that point. Not the velocity that happens between 2 points, but the velocity exactly at that point. The definition of instantaneous velocity is that it is the slope of the tangent line of the displacement graph. Remember the other day when we mapped out the displacement in the y direction, the shape of the position graph in the y resembled this parabola. So then the slope of that graph, or the tangent line of that graph, is the instantaneous velocity. So all you really had to know was that the orange vectors aren't going to be on the dotted line, but they're just going to touch it. And that resembles the velocity at that point. Now a couple of other things happened on this image. We said that in the x direction, the most important thing to remember is that velocity is constant. Okay, so v sub x is constant. So x direction, think of constant velocity. Y direction, think of constant acceleration. Okay, acceleration is constant, and that's due to gravity. At the top of the trajectory at point D, a couple of things happen. It's the halfway point of delta x, or the total horizontal displacement. It's also half of the total time t. At the top, at D, v sub x exists, but v sub y is 0. It's really confusing to think that the vertical velocity at D is 0, but the vertical acceleration is still gravity. So then from here, we moved on. We said, well, let's take a look at how we apply this information to solve problems. So for today, we had a lab to do. Pardon me again. And that lab was this pHet simulation. So for the pHet simulation, you had data that you looked at, and you had to solve using the kinematic equations first and then confirm the data that you got by running it through the pHet. So the first step is to do the calculations on the lab. So for the lab, we said, okay, for trial A gives us the vertical displacement delta y, the initial velocity of 18, and that little small circle here just means naught, and that means initial, so v naught. We don't know if that's in the x or the y just yet. And our launch angle is 0 degrees. Now that particular trial asks us to solve for delta x. So if you recall from your book reading, there's only one equation that exists in the x direction in kinematics, and that's delta x equals v sub xt. Now the reason for that is because in the x direction, acceleration is 0. So if v sub x is constant, then acceleration in the x is 0. Which means when we take our kinematic equations from one dimension and apply them to two dimensions in both the x and the y, our x equations, for example, delta x equals v sub I xt plus 1/2 a sub x t squared, would simplify to just delta x equals v sub xt. And the reason for this is because a sub x is 0. Many of the terms in our kinematic equations would either cancel each other out or just equal themselves. In this case, we don't have a difference between v sub ix and v sub fx because v sub ix equals v sub fx, so we just call it v sub x. So again, in the x direction, we just have this one equation. In the y direction, we still have all three of our other kinematic equations. So we have delta y equals v sub iy t plus 1/2 a sub y t squared. We also have v sub fy equals v sub iy plus a sub y t. And finally, v sub fy squared equals v sub iy squared plus 2 a sub y delta y. So I said 85% of the time we're going to need to solve for t in the y direction and then plug it in for x. Okay, solve for t in the y direction and plug it in the x direction. And that doesn't mean that it's going to happen this way all of the time, but most of the time this is what we're going to have to do. So back up to our first lab question. So let's organize the data that we have in terms of x and y. In the x direction, we're looking for delta x. We don't know v sub x just yet, and we don't know t. In the y direction, delta y is negative 10 meters. V sub iy and v sub fy will fill in just a second. Acceleration in the y is negative 10 meters per second squared due to gravity. And we don't know t. So if the Canon, and here I'll do my best to draw a Canon. If the Canon fires a cannonball completely horizontally, the vertical component of a velocity vector that is only horizontal is 0, right? There is no vertical component, which means that with this initial velocity here, v sub iy is 0, and the entire 18 meters per second is v sub x. So let's fill that in. So now it looks like we're down to two variables we don't know in the y. We don't know v sub fy, and we don't know t. But t we need to plug in the x. So I guess we are going to leave out v sub fy. If we leave out v sub fy, we're going to use the equation delta y equals v sub I yt plus 1/2 a sub y t squared, because this is the equation that leaves out v sub fy. So recall that from first dimension kinematics. Now, v sub iy is 0. So let's go ahead and cross this term out. And then we're left with delta y equals 1/2 a sub y t squared. If we multiply by 2 on both sides, that gets rid of the 1/2. And we get 2 delta y equals a sub y t squared. Divide by a sub y, and 2 delta y over a sub y equals t squared, or t equals the square root of 2 delta y over a sub y. When we plug in numbers, t equals 2 times negative 10 meters divided by negative 10 meters per second squared. The negative 10 meters and the negative 10 meters divide themselves, and we have t equal to the square root of 2 seconds squared. Now that, when you plug into your calculator, equals 1.4 seconds. So now we're going to take this t and plug it in here in the x direction. So in the x direction, we had delta x equals v sub xt. V sub x, we said, was 18 meters per second. T is now 1.4 seconds. Therefore, delta x equals 25.2 meters. So after you solved this is trial A, again from the lab, solving this using the kinematic equations, you would go to your pHet, click on lab, change the parameters of your lab such that they reflect what's outlined on the sheet. So here I have 0 degrees as my angle. My starting point is 10 meters up from my ending point, which makes delta y negative 10. I changed my initial speed to 18 meters per second, and I'll go ahead and fire the Canon. Then I'll move the bullseye to measure the delta x, and I get delta x is 25.6 meters. Okay, so by the pHet, delta x equals 25.6 meters. Now, a couple things for your lab. Remember, this particular lab is not due Monday. You always have at least a couple of days to work on the lab before turning it in. You need to do an abstract as outlined in the lab and a conclusion, and paste this into the lab book. Now, one more thing I wanted to go over really quickly was just how to use the pHet to view the vector dynamics. So if you click here on vectors, click on components and velocity vectors, you can fire in slow motion a projectile and watch what happens to the x and y components. See that y approach 0 and increase again in the negative direction. X remaining constant. I'll do that one more time. Fire the projectile, look at v sub x staying constant and v sub y diminishing to 0 and then increasing in the negative direction. Okay guys, so that is our video for today. I hope you have fun over the weekend working on the extra credit and hope you have a good weekend. I will see you soon.